So last week we discussed parameter estimation as an entry point to prediction and learning. We discussed a lot of things about parameter estimation. We discussed the difference between the situation where you have samples of your random variable and you are seeking a parameter, you are seeking the theory of your random variable. And then we discussed the reverse situation where you know the theory of your random variable, you know the distribution, you know all the parameters, and you have an observation about the random variable and you want to estimate the random variable itself, right? We discussed that together last time. We talked about how to qualify different estimators. Today, we will continue with the MMSE Linear Estimator. So this time, instead of having an observation, we have vector of observations. So we have some vector y, y1, y2, dot, 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 up to yn transpose. So last time we had a single observation. Now we have a vector of observations. And throughout that vector of observations that tells something about x, we want to get the optimal estimator of x. All right? So here we are still in the linear case. So x hat, our estimator, function of this vector y, is A transpose y plus b. All right? That's just some linear estimator. A transpose y is a vector or a scalar? What's up? Is this a vector or a scalar? Yeah, of course. You don't need to think A transpose y. So A transpose y is a scalar, and you would guess it has to be a scalar because you are estimating a scalar x, right? So you are estimating a scalar, your estimator has to be also a scalar. So it's a function of a vector that gives you in the end a scalar. All right, again, we have this expected error is the expected value of x minus g of y squared. What do we want to do with this thing for our estimator, which is the expected value of x minus A transpose y minus b over all square? What do we want to do with this? Pick it up. We talked about this last week. What do we want to do with this to get to our estimator? Yeah, this is the error. We want to minimize it, right? So we want to minimize this in order to get to our estimator. All right. Okay. If we call this random variable z, this becomes an estimation of z through a constant, right? We did this case together last time as well. What will the optimal value of the constant be? What will b star be? It will be the expected value of z, which is the expected value of x mx minus A transpose my. All right? This is also something we talked about last time. You are estimating a random variable with a constant. You don't really have many options, right? It's the expected value. It's just a constant, right? Okay, now we have an idea about E. E is becoming function of A alone, which is the expected value of x minus mx minus A transpose y minus my. Great. Everything is now becoming function of A as the only variable in the equation. What shall we do with this to minimize it? Exactly, we want to differentiate this with respect to A. Oh, okay, but A is a vector. All right, so we open our usual bracket, but this time it is for something very important. It is in the body of the course, and we will talk about the gradient and the Hessian. How many of you heard about these terms before? So nobody heard about the gradient or the Hessian before? Okay, except for one. So two. What are we going to do here? Why do we need that? Because we are differentiating a vector, right? We are differentiating with respect to a vector. So that's not just a scalar quantity. So we need these. So Suppose that we have f of x, which is f of x1, x2, dot, 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 xn. The gradient with respect to x, fx, is partial fx by partial x1, partial fx by partial x2, dot, 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 partial fx by partial xn. And the Hessian of this fx, I'm going to write it in a format that differs from what you have in your notes. Partial fx squared by partial x1 squared, partial fx squared by partial x1, x2, and partial fxn squared by partial x1, partial xn. And then the second row, once again, but this time it will be x2, x1, and here x2 squared, dot, 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 and the last one is x2, xn. And you can complete the rest of terms. So what exactly is going on here? We have two differentiation operators. The first operator, this one should be transposed. The first operator takes a function and gives you a vector of derivatives. The second operator takes a function and gives you a matrix of derivatives. First of all, what is this vector of derivatives is? You have function that has all of these variables. The vector of derivatives is the differentiation with respect to the first, the partial differentiation with respect to the second, going on until the nth. How about this one? For the first vector, it is the second partial differentiation to x1, and then x1, x2, x1, xn, 2, 1, 2, 2, and 2n. All right? Is that clear? Can someone tell me, can someone write this Hessian in terms of a bunch of gradients? Can someone write this in terms of a bunch of gradients?
Multiply two gradients. Matrix form.
Yeah, but the multiplication is, assuming that the operator will operate under multiplication. But can you just write it immediately as each row of these is some gradient or of something? How about this row, for example? Can we write this as some gradient?
Gradient of del fx by del x1.
Transpose. But yeah, exactly. So this is the gradient with respect to x, right? As our friend here said, the partial fx by partial x1 transpose. And this is the case for any row, so you can actually remove this and write I for row I. All right? Everybody's okay until now? All right, so let's return to this problem. We want to get the gradient with respect to A of this E. And this will end up being 2 times the expected value of x minus mx minus A transpose y minus my multiplied by y minus my. When you look at this, I mean, the fundamental idea, it ended up being quite the same like traditional derivative, right? So you have something here squared, 2 minus sine, the differentiation of what you have inside, which is what you get here. All right, so at A equals A star, this guy is supposed to be 0. And thus, let's look here in order to get A star. What happens when you enter this term here under the expectation? What do you get? First of all, let's try to manipulate this a little bit. Is this a scalar or a vector? This is also a scalar. So these three terms together, I can manipulate them and just write them like this. Y minus my times y minus my transpose A. Do you have any problem? That is a scalar. I can transpose a scalar. I can shift its order with the vector. I can do whatever I want. That's completely fine, right? When you enter the expectation on this term without the A, what do you get? We also did this. What is the expected value of y minus my, y minus my transpose? Exactly, right? But the covariance matrix, right? Okay? So this is ky. When you enter the expectation, this ends up being ky. And thus you can see that A star is ky inverse multiplied by the expected value of x minus mx y minus my. And thus the last substitution will give you this optimal estimator we are seeking, g of y, which is ky inverse this expected value of x minus mx y minus my overall transpose times y minus my plus mx. Don't get overwhelmed by the too many terms and it looks too complicated. If that was a scalar, y minus my, this expectation of x minus mx, y minus my would have been what? Covariance, right? And this would have been what?
Variance.
1 over variance, right? So when you substitute the terms, you end up with the exact same relation as the linear relation we had. So don't get like, oh, there's too many terms. It's quite simple. When you look at this thing all together with the exception of mx, what is the mean of this? This is some constant, right? So what is the mean of this? 0, exactly. So the mean of this thing all together is mx. Remember that you are trying to estimate x hat. You are trying to estimate x, through x hat. So you want the expectation of your estimator to be the expectation of the parameter you are trying to estimate, right? So the expected value of this thing all together, because the expected value of this will go away, this is the expected value of your estimator, the expected value of x hat. How about the orthogonality property that we talked about? Remember that this is the error, again. This is a normalized version of the observation, again. So if this normalized version is y hat, you would say here, this is a vector, you would say here that the expected value of the error times your y, say y prime, is 0. All right? The expected value of the error, this is the error, multiplied by this normalized version of y of the observation is a 0 vector. All right? Any problems with that? It's quite similar to what we did last time. Okay? All right. So, but until now, we have been assuming that our estimator is linear. Let's look at the MMSE Generalized Estimator. So the MMSE Generalized Estimator is also called nonlinear estimator, but I hate this nomenclature, and we will show by example why. So let's call it generalized. But what they meant here by calling it nonlinear is that they meant that the linear assumption is not there. So you can have anything. That's what they meant. So now we don't really have any assumptions, so we are solving this problem. We want the argument that minimizes this error, x minus g of y squared. That is flat out our problem. We want to minimize this expected error. We want to find G that minimizes this expected error. No assumptions. There's no assumption we put here at all. Okay, let's try to think of this through the total expectation. So this expected value of x minus g of y squared is essentially the expected value of over y, this expected value of x minus g of y squared conditioned on y. Do you remember that? Do you remember the total expectation theorem? If you replace this with x, it's the standard format we have seen before. The expected value of x is the expected value over y, expected value of x given y, right? I did nothing other than replacing x with x minus g of y squared. Everything is okay until now? So what is this? What is this term? Thus, the expected value we are seeking, x minus g of y squared, is some integral, because of the expectation, integral over y, this term. So we want expectation over y. So it's whatever inside times fy of y, right? Just functions of random variable, direct substitution. So this thing, the expected value of x minus g of y squared given y, fy of y dy. Right? Here y is a specific value. Y equals small y. All right. How do you think about this random variable? G of y given y equals y. This random variable combined. What is this? What can you say about this? So this guy is a constant, right? There's no more randomness. Randomness, gone. So this is a constant. You can actually call it A. Okay? What can you say about fy of y? It's something always positive, right? So in order to minimize this thing, which means to minimize this thing, your goal can be only centralized about minimizing this for every single possible value of y. So the problem is converted to, so the new problem is about minimizing the expected value of x minus g of y squared given y. Or given y equals specific y, just for clarity. All right? And this thing, we have just said that it is a constant. Have we seen this problem before? We did this problem like 3 times. Well, this is that you have a new estimator of your random variable, and that new estimator is a constant, right? So in that case, what is the optimal solution? What is A star? Yeah, that's the only thing missing. That's the only thing missing, exactly. So it will become an expectation. So it is g of y equals, as our friend here said, the expected value of x given y equals y. This is also valid for the case of the vectors. If you have vector of observation, it is the same thing. No need to go through the same derivation. What is more important than the math written on board is actually what does that mean? What does that mean? This is a tracker of x based on the value you have for y. For every single possible value y equals y, you are trying to track x through its conditional expectation. For every single value of y, you are trying to track x through the conditional expectation. So having some estimator that is essentially an expectation isn't a bad thing in itself. I mean, it just depends on what is going on. In the past, when we tried to estimate through an absolute constant, it ended up being the expected value of x, which was a terrible estimator. This one is a good estimator, though. This is conditional expectation. So it takes into account the information y is giving you. That is why it is a line tracker, not a line, it's an estimator tracker of x based on y. All right? Last question before we start doing an example. Do we have this? In this problem setup, do we have this? It just looks like some e of x given, what is this? I need a function. Do we have this? Do we have the ingredients to get this? We have all of them. We have all of them. Think about a problem like this, the one you did in your homework. You had the distribution of x, the distribution of n, the distribution of y. You had all the distributions. You have all of these. So you can definitely get this expectation, right? This expectation is going to be just that the value x under some integral times f of x given y dx. Right? And you have all of this. All of these terms are available. Right? Okay, so let's give an example to see what is going on with these two different types of estimators we did, the linear one, the nonlinear one, the quality of each of them through an example. So, example 1, you have x and y, joint random variables, and you have f xy of x and y equals 2e to the minus x e to the minus y, 0 less than or equal to y less than or x less than or equal to x less than infinity, and it is 0 otherwise, no need to write that. The first part of the question asks to find the marginals. The second part of the question asks to find mx sigma x squared, my sigma y squared, and rho xy. And then to find optimal linear and generalized estimators for x from y, and to find optimal linear and generalized estimators for y from x. The first two parts you know very well how to do. That's not the time nor the place to do them, so let's write them immediately. Fx of x will end up being 2e to the minus x, 1 minus e to the minus x, x greater than or equal to 0. Fy of y will end up being 2e to the minus 2y, y greater than or equal to 0. Mx for part B will be 3 over 2 sigma x squared. The variance is 5 over 4. My is a half. Sigma y squared is 1/4. And rho xy is 1 over square root 5. I'm assuming nobody's going to be having any problems with this, right? So joint PDF, integrate on one variable to get the other expectations, some just calculus, shouldn't be a problem, all right? Good, so let's find the linear estimator for the case of you want x from y. X hat is rho xy sigma x sigma y y minus my plus mx. You remember that from last time? You remember that from today? We just did it for a vector, so it just looks the same thing, just a bunch of substitutions, and it will end up giving you x hat equals y plus 1. Generalized, we want small x hat, which is the expected value of x given y equals y, which is the integral. How can we do that? Can someone tell me what should we put here? What should we put here from all the terms we have here? It's expectation of x. So first of all, it's x times something, right? How can we get this? The conditional PDF, how can we get this?
Joint over PDF of y.
Exactly. So joint over marginal of y, thank you. We have this, and we have this. So it is 2 e to the minus x e to the minus y over 2 e to the minus 2y. And then you are integrating to get function of y, so it's dx. The thing remaining will be, what is the integration limits? Can someone tell me, where is this area? This is the line y equals x. Where is this area? Exactly, the area between the x-axis and the line. Right? Okay? So this integral will end up being from x equals y to infinity. You have these terms together, so x hat is the integration from x equals y to infinity, e to the y, x e to the minus x dx. Of course, I'm not going to do this integral. How can you do this integral? What's up? Yeah, integration by parts, right? It's a standard type of integral. And then when we do this thing, you end up having y plus 1, and thus capital X hat is y plus 1. What is going on here? What is going on? Look at this and look at this. What did we end up having here?
You said that generalized form also satisfies linear.
Yeah, thank you, exactly, right? First of all, we realized that the linear is optimal. Second of all, as she said, we realized that the generalized is the same as the linear, and it is y plus 1. So this already tells you why I don't like the naming non-linear MMSE. Because, yeah, it ended up being linear here. Okay? Is it always the case? Let's do it the other way around. Linear. And let's try to do this in a faster way. Y hat is rho xy sigma y over sigma x, x minus mx plus my. It will end up being 1/5 x plus 1. And then the other one, y hat is integral. We can do it immediately, y. And this time we want f. This one is going to be f of y given x, y given x dy, which will be the integral y equals 0 to x, y 2 e to the minus x e to the minus y over 2 e to the minus x 1 minus e to the minus x dy. These terms cancel each other. Again, integration by parts. Once again, I'm not going to do it in detail. So the final answer will end up being 1 minus x e to the minus x divided by 1 minus e to the minus x. And thus y hat is 1 minus x e to the minus x, 1 minus e to the minus x. Is this linear? Obviously, no, that is country miles away from linearity, right? And this guy is linear. How could you plot something like this? I'm saying how. I'm not saying what will it look like. But how could you plot something like this?
Zero crossing, then between them, first derivative and the second order derivative.
Yeah. You said actually more than what I thought. Thank you so much. Exactly. So she said multiple extremely useful things. So number one, the limits. What happens at 0, what happens at infinity, and points in the middle. Number two, derivatives to see the arc, whether it will be concave or convex, which is something we will do together today. So let's have a quick look at the difference between the two estimators, and then we will move on to something, to the last thing actually we want to discuss in the lecture of today. So when you do exactly what she said, you get a line that looks like this, and the other estimator, that one for the first estimator, that one is for the linear one, and the nonlinear one looks something like this. What is this telling you? Obviously, it doesn't go down. What is this telling you about the linear estimator? It is doing fairly well here, fairly well. But as the values get larger, it will start to do terrible. The line will leave it off. It almost saturates. It will not do well for you. All right? Okay. Now we will shift gears to a different topic. It is connected, but it is still a new topic, linear least squares. So suppose you have n points in a k-dimensional space. And these points where n is greater than k, and these points are of the form xi transpose equals xi1, xi2, xin, 1 less than or equal to I less than or equal to n. And you want to have a line that minimizes the error, and that line has the form beta 1 x1 beta 2 x2 beta n xn equals y. Forget about all this. Let's talk first about what is the meaning here. What are we going to do here? Let's return again to the standard problem of machine learning. The standard problem of machine learning is that you have data, right? You have data points. Input, output, input, output. But then, since you cannot have all the data points in the world, you need to derive some function based on this input, output to learn how the output acts in terms of certain input to the system, right? That's a standard machine learning problem. You have data, and you want to learn the missing data, right? You have certain inputs, certain outputs. You derive a function that could tell you what will the output be for inputs that are not in your training set, right? The linear version of this problem is called the linear regression, and that's exactly what we will be doing here, okay? Let's try to do it, to formulate it in a mathematical manner, in a simple mathematical manner. We have here x1, x2, and suppose you have these points. All right? Suppose you have these points. Suppose that your input is x1, your output is x2. x1 here, x2 here, x1 here, x2 here, for this point and this point and this point and this point, and you want to derive some function that should give you the different values of x2 for any x1. For example, you don't have any value for this particular x1. All right? What we want to do here is we want to do this in a linear manner. So we want to pick a line, that line that goes like this, for example, such that the line is the closest representation of the data, the closest we can be. What does the word closest mean here? How can we formulate it mathematically? Exactly. Again, that minimizes the differences. One way is the way she said, which is actually the way we will do, minimizes the squares of the differences. All right? Is the setup clear? So here, n equals 9, k equals 2. All right? Let's write the setup again. So the goal of the problem we are trying to handle here is to reach argmin over beta, the norm of the matrix X, beta minus Y. And we will pick norm 2 here because it is pretty much the best metric you could operate with. All right? What is the matrix X? So here, when you look at this data point, if you have it written as beta 1 xi1 plus beta 2 xi2 dot 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 plus beta n xin equals yi, this is a row of the matrix X, row I. Multiple things, quick things before we do the math. What happens when you only have two linearly independent data points? So instead of 9 in this example, you only have 2. Yeah, you have an optimal solution. You have an optimal solution. If you have 2 points, there exists a line passing by any 2 points. And if the line is literally passing by the 2 points, the error is 0. So that's like the ultimate optimal. You will not need to do any of this because you are essentially solving 2 equations and 2 unknowns. You will get the coefficients. You have your line. Life is good. No error. Right? So in case you have 2, problem solved. Then the other thing I want to mention is that this problem is not particularly brand new for you. You have already seen this problem in another format, but that format wasn't particularly that you have points and you want to get coefficients. You had it in the format where you want to find this solution actually. So you have a variety of lines that don't intersect and you want to find the point in the middle that minimizes the distance to every line. So you had this before in the linear system of equations Ex equals B. Right? You had this, it's not something brand new, but now we are reverting it. Instead of searching for the points, these lines now represent the points, and you are searching for the line. It's the other way around, but it's not something brand new to you. Okay? Obviously, this matrix is a tall matrix. So we will study a special case in example 2. Last example in the first lecture is called ordinary least squares, OLS. And here, the matrix X has full column rank. If a matrix has full column rank, what is this telling about its null space? What can we say about the null space of X? So everyone, 0, yeah, thank you. Everyone knows what the null space is, right? I don't need to go that backward. So yeah, it's as she said, the null space is 0 because with some row operations, you could get to a situation where you have identity here, right? And under that setup, when you are trying to solve this equation, the only solution will be the first is 0, the second is 0, third is 0, everything is 0, all right? So the null space of a full column rank matrix is 0. This is a condition to simplify our problem, because otherwise we will need to give like 5 lectures on this. We cannot. We need to do it in like 1/3 of a lecture. So what do we need to do here? What is this guy? X beta minus y squared under the norm. I can write it like this. Anybody's having issue with that?
Can I ask a question?
Yeah, of course.
I'm surprised why we write 2 underneath.
It's norm 2, that norm I mean. The L2 norm. Square root, first entry square, second entry square. Because if I write 1, it will be the L1 norm, will be summation of absolute values. Right? These 2 norms are not the same. We picked this particular norm because it is a more valuable, more accurate metric about the distance. Okay? So, anybody's having an issue with this? I just like wrote it as vector transpose vector. Okay? So what is this? This is beta transpose x beta plus or minus for that matter, beta transpose x transpose y minus y transpose x beta plus y transpose y. The thing we have been doing forever now, how to minimize this? Again. What is the step we need to do to minimize this? Yeah, exactly. But again, it is the gradient, right? So take the gradient with respect to beta of this x beta minus y norm 2 squared equals. Okay, there is something you can get intuitively. Can someone intuitively tell me what is the gradient of x transpose x? Just by the intuition. Who said 2x? Yeah, exactly. Yeah, this is 2x. Immediately by intuition, he thought of this as x squared. It ends up being 2x. It actually is 2x. Why? Because this guy is this, right? x1 squared plus x2 squared dot 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 plus xn squared. When you try to get the gradient of this differentiation with respect to the first 2x1, second 2x2, 2xn, overall transpose is 2x. Right? Any problems? X here is constant with respect to beta. You're taking the gradient with respect to beta, so this will end up being 2 x transpose x beta. Okay. You already know this will go away, not function of beta. Anybody is having an issue with the following statement? This guy and this guy are the same. Who says yes? Who says no? I'm saying this and this are the same.
Yes.
Who said yes? Anybody is not agreeing? This is a scalar. can transpose it, you can you can do whatever you want. This is a scalar, you can do anything to it. And when you transpose this thing, you get this thing immediately, so they are the same. So for the derivative, you can just differentiate one of them and multiply by 2, and that differentiation could easily be seen as minus x, or x transpose y, times 2. All right, what is x? What is the beta that minimizes this? It will end up being x transpose x inverse x transpose y. So this is the beta that has the coefficients that solves for you the optimal linear regression. Optimal linear regression. Why is it called regression? Because you are trying to minimize the errors. You make the errors or the distances regress. And then one last thing that's also very important, but unfortunately we don't have time to discuss every single important thing. If you had this, and this is a square matrix, full rank square matrix, what would have been the solution? How would you do this? Linear system of equations. How would you do this? What is y? What is, sorry, beta for this equation? Yeah, exactly, right? It's a square full rank matrix. Its inverse exists, right? What is the only problem we have here? Is that we have more equations than unknowns. So the straight inverse matrix is not even square, right? So what is the solution here? As our friend said, it's x inverse y. Oh, this is something that could intuitively look like something inverse, right? Actually, this thing, which is also very important, is called x plus equals x transpose x inverse x transpose, and it is called more Penrose pseudo-inverse. So actually this guy is sum inverse, but it is pseudo-inverse because the matrix is a long matrix. And if we had time, we would have discussed this a little bit, but yeah, this thing is called more Penrose pseudo-inverse. So the optimal solution for the linear regression ends up being the pseudo-inverse times y. Okay? All right, we will return again in 10 minutes.